right, so we're going to be moving on to the second part of this unit. It's actually 2 chapters in your textbook combined into 1 unit. We're still looking at applications of derivatives, but we're going to start looking at extrema, so maximums, and minimums. Now, before we get into that, we're going to take a quick look back at interval notation, and we're going to look at it specifically in terms of x values or the domain of a function. And this is just because we're going to be using it throughout this section or this part of the unit. So I've got some diagrams drawn here. We're going to write out what it would look like in set builder notation. I'm not going to write out the full set builder notation, and then we're going to write it out in interval notation. So for the first example, we have x being greater than 3 and less than 7. Remember, the open circles means it's not included. So if I were to write that in interval notation, I'd have 3, 7 in round brackets. If x is greater than or equal to 3 and less than or equal to 7, then we'd be using square brackets. If x is greater than 3 and less than or equal to 7, round bracket for 3, square bracket for 7. Another example, x might be getting bigger than or equal to 3, or x is greater than or equal to 3. Typically, we would write it this way: x is greater than or equal to 3. Then that means our low point is 3, and our high point is infinity. And the last one, if x can be anything on the x-axis, then we would say x is the element of reals. Or if we're doing interval notation, we're going from negative infinity to infinity. So I'm confident you guys are probably already fine with interval notation, but I just wanted to do a quick refresher because we're going to be using it throughout the rest of this topic. All right, so the first thing we're going to talk about are extreme values, and another name for that is just maximums and minimums. So before we look at the diagram, I just want to look below at the definitions. The first definition is for absolute maximums and minimums. So these would be the points where the function has the highest or lowest y value. But we can also have local maximum and minimums. And another way or another term for that is relative maximum or minimum. And so that's where that's a point on the graph where the graph changes from increasing to decreasing or decreasing to increasing, but it's not the absolute maximum or absolute minimum. So if the graph is changing from increasing to decreasing, then we would have a local maximum. So the graph is increasing, graph is decreasing. Or if the graph is going from decreasing to increasing, then we would have a local minimum. So decreasing and then increasing. So with that in mind, we're going to go back to the diagram up here and take a look at where our absolute and local max and mins are. So if we look at A has a high point, the graph is decreasing, so that meant if this graph had continued, it would have gone from increasing to decreasing. So this is a local maximum. B is the highest point on the graph, so that's an absolute maximum. C is the lowest point on the graph, so that's our absolute minimum. D would be a local max. And E would be a local min. So if those terms are confusing for you because they are brand new, certainly rewind this, take a look at it again before you move on. All right, so example number 1 here. So we're just going to look at points where the graph is increasing and decreasing. So increasing would mean that our derivative or our tangent line would be going in a positive direction. If it's negative, that means our tangent would be going in a negative direction. And again, there. So we're looking at where the graph is increasing and decreasing. Now, if we're writing this out in interval notation, any of those turning points would be considered critical points, so they would not be included. And so we would have the graph increasing from -3 to -2 and from 1 to 3. Now, some people will use set notation where they'll actually put the union symbol in between. Okay? But I'm not going to worry about that too much here in grade 12. All right, if we're looking at where the graph is decreasing, the graph is decreasing from -2 to +1. And again, we're not including the critical point, so -2 to +1. The function is neither increasing or decreasing when our slope of the tangent line would be 0. And so that's happening at x equals -2. and at x equals 1. And I've already mentioned this word throughout, but those would be called our critical points, or you'll hear some people call them critical numbers. When we find our critical numbers, there's always a potential that a max or min value could occur at those points, either local or local or absolute. So for example, if I was looking at the point -2, if I'm looking at the point where x is -2, the graph is increasing on the left-hand side and decreasing on the right-hand side. So this would be, in this case, a local maximum. Okay, if we were looking at point 1, the graph is decreasing and then increasing. In this case, we know it's a minimum. And looking at the graph, we also know it's the lowest point in the graph, so it would be an absolute minimum. All right, let's talk a little bit about Pierre de Fermat. So Fermat was a famous mathematician. He was actually a lawyer as well back in France. And he has quite a few theorems out there, but this is one that pertains specifically to calculus. And so Fermat's theorem can be used to find maximums and minimums of functions. So this is his specific theorem. It says if f of x has a local maximum or minimum at x equals c, c being our critical point, then either the derivative of c, so f prime of c equals 0, so the value of the derivative is 0, or the value of the derivative does not exist. And one way to write that is using this notation here. So the backwards e actually stands for exists. If we put a does not equal sign in front of that, that means does not exist, or sometimes people will write it this way. Again, I'm just exposing you to the notation. It's okay if you're not familiar with it. Now, something to note, if the derivative does not exist, that would mean there would be either an endpoint, a kink, a sharp curve, an asymptote, etc. So we're going to look at some examples of critical numbers. So if you're asked to find the critical numbers of the following functions, the first thing you're going to do is take the derivative. So f prime of x would equal 3x squared plus 12x plus 9. We would factor it. So start by pulling out a common factor. And then we look at the two cases. We look at where the derivative is equal to 0, and then we look at possible restrictions. So for our critical numbers, this would be where f prime of x equals 0. So if we set this equal to 0, 3 times x plus 3 times x plus 1, x is going to equal -3, and x is going to equal -1. So these would be our critical points. Now this is a polynomial function, so that means there's no restrictions. So there's no place where the derivative wouldn't exist. All right, on to the next one. X minus root x. If you need to, write that out as x minus x to the 1/2. If we take the derivative, we're going to have 1 minus 1/2 x to the -1/2, which is the same as 1 minus 1 over 2 root x. So if we consider the case where f prime of x equals 0, we would have 1 minus 1 over 2 root x equals 0. So 1 equals 1 over 2 root x. 2 root x equals 1. Root x equals 1/2. And so when we square both sides, x equals 1/4. So that would be one of our critical points. If we look at this question, we have a root x, which means there are some restrictions for x. And so if we set this equal, we have 1 over 2 root x cannot be 0. So 1 over 2 root x cannot be 0. So we're looking at our derivative. Okay, so we're looking at our derivative right here, and there would be a restriction there. Essentially, we're looking for a non-permissible value. So 1 over 2 root x cannot equal 0. So we solve the equation. Actually, sorry, we don't need to worry about the 1 here. We're just looking at the 2 root x. So 2 root x, sorry for that. 2 root x cannot equal 0. So we divide by 2. Root x cannot be 0. If we square both sides, x cannot be 0. So we're going to have an asymptote at x equals 0. So that would be another critical point. And for the last one, we have f of x equals t over t squared plus 1. So I'm going to be using the quotient rule for this one rather than using the chain rule with the product rule. So if you remember with the quotient rule, we're going to have t squared plus 1 times the derivative of t, which is 1. And I'm just going to erase the section from before. T squared plus 1 times 1 minus t times the derivative of t squared plus 1, which is 2t. And then it's all over t squared plus 1 all squared. Now, simplifying that down, we're going to have t squared plus 1 minus 2t squared all over t squared plus 1 all squared. Simplifying that down, we're going to have negative t squared plus 1 all over t squared plus 1 all squared. Now we consider both scenarios. I'm just going to erase some of this earlier stuff. Consider both scenarios. First is when f prime of x is equal to 0. So we would have negative t squared plus 1 all over t squared plus 1 squared equals 0. So multiplying, we're going to end up with negative t squared plus 1 equals 0. So 1 equals t squared. And when we square root, remember plus or minus, t has to equal plus or minus 1. So those would be one set of our critical points. So that would occur when the derivative is equal to 0. We also have to consider our restrictions. We have t squared plus 1 squared in the denominator. So t squared plus 1 all squared cannot equal 0. So what we're looking for is when f prime of x does not exist, if we're using that notation. So solving here, the first thing we would do is square root, and that gives us t squared plus 1 cannot equal 0. Subtract 1, t squared cannot equal negative 1. At this point, we would square root, and we can't square root a negative, so there are no restrictions. So our critical points would just be t equals plus or minus 1. Again, if you need to go back and review probably B and C, then back up the video, pause, back it up, and then move forward. All right, so I've got another theorem for you here, and this is the extreme value theorem, and it says if f of x is continuous on a closed interval, that means we have a definite starting point and ending point, or we've got two endpoints, then f of x has an absolute maximum and an absolute minimum. So we're talking about a graph that actually has a starting point and an ending point. It's not going on and on forever in one or more directions. So we're going to look at this example here. It says find the absolute maximum or minimum for f of x equals x cubed plus 6x squared plus 9x plus 2 over the interval negative 3.5 to 1 inclusive. All right, so the steps that we would follow, the first thing you're going to do is find your critical points. And so that means we're taking the derivative. So 3x squared plus 12x plus 9. And we'll be factoring. We actually just factored the same one on the last page. So pull out a 3x squared plus 4x plus 3. 3 times x plus 3, x plus 1. Now looking for our critical values. We're looking when f prime of x equals 0. And since it's a polynomial function, there's no restriction, so we don't have to consider when it doesn't exist. But we would have our critical points at x equals negative 3 and x equals negative 1. So we're looking at a cubic function, okay? And if you remember some of the properties of cubic functions, it means it's going to be looking something like this. But we're looking at the points from negative 3.5 to 1. All right, once we have our critical points, then we find what the values are at that point. So we're plugging it back into our original function. So for the first one here, we're finding out the value of f of negative 3. So we would have negative 3 cubed plus 6 times negative 3 squared plus 9 times negative 3 plus 2. So f of negative 3 equals 2. And then if we look at f of negative 1, f of f of negative 1, sorry. So f of negative 1 would be negative 1 cubed plus 6 times negative 1 squared plus 9 times negative 1 plus 2. F of negative 1 would be negative 2. So if I was to write out those coordinates right now, I've got negative 3 comma 2 and negative 1 comma negative 2. So those are points that may or may not be our maxes and our mins. We don't know, and we won't know until we compare our endpoints. So we also consider our endpoints. So find the values of f of x at the endpoints. So we have an endpoint of negative 3.5. So f of negative 3.5 would be negative 3.5 cubed plus 6 times negative 3.5 squared plus 9 times negative 3.5 plus 2. So f of negative 3.5 equals 1.125. Now you can certainly convert that into a fraction, but right now for comparison purposes, I'm going to keep it as a decimal. So that would mean one of our coordinates is negative 3.5 and 1.125. And then the last thing we would be looking for f of 1. And if I were to sub f of 1 through, I would get 18. So my other point is going to be 1 comma 18. Now, once we have our values at the critical points and our values at the endpoints, we're literally just comparing our points to see which ones would be our maxes and our mins. And so if we look at the note here, it says the largest of the values from steps 2 and 3 is the absolute maximum. So our largest y value would be the absolute maximum, and the smallest y value would be the absolute minimum. So again, we're looking at the y values. So if we go through and look, we've got a y value at 2, negative 2, 1.125, and 18. So this one here is going to be our max, our absolute max. And then if we look for our y values, our lowest y value is here. So this is going to be our absolute min. So we're going to write this as absolute max at 18 when x equals 1. And we have an absolute minimum at negative 2 when x equals negative 1. All right, so we're going to do a couple more examples, more so just to get some practice with taking the derivative of different types of functions. And then hopefully that'll give you enough examples to work through these. If you want to, maybe pause the video, try the example, come back and check it out, and then do the same with the next one. So example number 4 says find the absolute max and min values for each of the following functions. We're going to take the derivative here. Again, it's a polynomial function, so we won't have to worry about restrictions. 6x squared minus 6x minus 36. Pull out a common factor. And 6 times x minus 3 times x plus 2. So our critical points when we set that equal to 0 are going to be x equals 3 and x equals negative 2. Now, once we have our critical points, then to determine our absolute max and mins when we're on a very specific interval is to first plug in our critical points into the original function to see where those coordinates are. So f of 3, I'm going to save you some time here and just have you trust me that when I sub these in, I'm going to get the values I show you. But if I plug in 3, I'm going to get negative 19. If I plug in negative 2, I'm going to get 106. So these are my critical points, or critical numbers. And then I also have to sub in my endpoints. So negative 3 would give me 89, and f of 4 would give me negative 2. So these would be my endpoints. So writing out those coordinates, that's 3 and negative 19, negative 2 and 106, negative 3 and 89, and 4 and negative 2. So if I'm looking for my absolute maximum, I'm looking for the largest y value. So that's going to be right here. So this is my absolute maximum. So we'd say I have an absolute maximum at 106 when x equals -2. And my absolute minimum would happen at 3,19. So I would say I have an absolute minimum at -19 when x equals 3. All right, one more question. This one will be a little trickier with regards to the derivative. So again, if you want to pause the video, try it for yourself and then come back. We'll take a look at the derivative first. So f prime of x. We're going to use the product rule here. So x to the 2/5 times the derivative of 5 plus x, which is 1, plus 5 plus x times the derivative of x to the 2/5, which is 2/5, times x to the -3/5. We're going to simplify that down. X to the 2/5. I'm going to multiply this through. Gives us 2 times x to the -3/5 plus 2/5 x to the 2/5. Keep simplifying. X to the 2/5 plus 2/5 x to the 2/5 is actually 7/5 x to the 2/5 plus 2x to the -3/5. So we need to factor out a fraction here. Remember that 7/5 is the same as 1/5 times 7. So we're going to factor out a 1/5. And we're going to factor out x to the -3/5. And that's going to leave me with 7x plus 10. Now, if I set that equal to 0, that means that x will either x equals 0 or x equals -10/7. Now we do still have to check for restrictions, because if I rewrite this, this is the same as 7x plus 10 all over 5 times x to the 3/5. Well, when x is in the denominator like that, we know that x cannot be 0. So this will be a critical point, but it's going to be an asymptote. So x cannot equal 0. All right, so we'll have critical points at x equals -10/7 and x cannot equal 0. And so if we plug in all of our values here, we're going to have f at, we're going to plug in -10/7. So we're going to have -10/7 to the exponent 2/5 times -10/7 plus 5 would give us a point of -10/7, comma, again, I'm going to leave this as a decimal, 4.1, and then I'm going to check out the other points as well. So I'm going to have -5 to the exponent 2/5 times -5 plus 5, which is 0. So we're going to have -5, comma 0. And then we'll plug in the other one. 1 to the 2/5, so that's 1 times 5 plus 1, which is 6. We're going to have 1, comma 6. So looking at these points here, again, we're looking for our absolute max and our absolute min. So our highest y value happens here. So this is going to be our absolute maximum. And then we're going to have an absolute minimum right here. All right, so hopefully that gives you enough information, enough practice. Have a good night, and we will see you soon.